Alrighty. So, today we're finally going to start talking about transactional memory in C++. And boy, my handwriting is really bad. Let's see if I can... There we go. Okay. So this is going to be like a multi-part series. And many apologies, untranslatable metaphor. I know this has taken a while. I know you've been asking for this for months, but we're finally getting it. So I have to stop at about 45-ish minutes for YouTube to do its thing with converting to multiple languages. So we'll stop the stream and the recording at about that point, and this will be part 1, and we'll go all the way to part N, whatever that looks like. So given that this is the first piece, let's try to start at the beginning. And as always, I'm not the knower of all things. I'm going to miss a whole bunch of stuff. And my goal here is not to try to inflate my participation in this. It's more just to share. I got involved at some point. Here's where I got involved. Step N, whatever that is. It's not step 1, I'll tell you that much. It was much later than when Morris and Near originally started this. But at some point I got involved, and then I'm going to mostly share the things that I worked on and some of the stuff that I saw. Again, this is going to be super incomplete, but hopefully this gives you a sense of what I think of transactional memory, what I think of C++. And for those of you that may be interested in working on advancing standard languages like C++ or C or other languages where you have an actual sort of standards body, this might give you some sense of what that looks like. Okay. Now, almost as always, I want to just give a small shout out to Dream Clinic, my friends over here. I love their stuff. I really do. This just came out, 8 hours ago, and yeah, I'm gonna be listening to this on repeat for sure. So if you like this kind of music, check them out. Subscribe, like, all that. I generally don't ask for these things for GTT, but for my friends over at Dream Clinic, yeah, give them a sub or like or something. Okay, so starting at the beginning, I want to start first by talking a little bit about this gentleman who I'm extremely lucky to be able to call one of my mentors, advisors, sort of like in some capacity one of my academic fathers or parents. He was on my dissertation committee. My true sort of like official academic parents are Jeremy Seek and Manish Bhattacharjani. Those were my advisors and co-advisors, but Morris got involved peripherally, and he was on my dissertation committee, and I've continued to work with Morris for the last almost 20 years, and absolutely love this guy. He's taught me tons, and this is a little bit about him. His academic parent is Barbara Liskov at MIT, I believe. I think she just recently won, or maybe several years back, she won the Turing Award. I kind of have a sneaky suspicion that Morris is going to win the Turing Award. And he's won the Dijkstra Award like many times. And I don't know that Morris actually cares about such things, but his contributions to the field have been enormous. And in addition to inventing transactional memory, along with Nir Shavit, I think these two folks are generally credited as inventing the field of transactional memory. Morris is sort of the general field of TM. And I think Nir spearheaded the software transactional memory movement, something like that. And I think the original paper, I think it was Morris and Elliot Moss, maybe. And yeah, so I don't want to go too far down that rabbit hole, but it started basically with these guys. And I wonder, yeah, so he also invented linearizability. I can't talk today, so you're gonna have to bear with me. Linearizability, yeah, and here we go, as well as hardware, software, transactional memory, and he's at Brown and all that stuff. He's also just a very cool guy. He's in my experience, he's very humble. He's fun to be around. He's super famous, but you would maybe never get that from talking to him in real life. I think I remember one time I was at Brown, since Halloween's coming up. I think I was at Brown for, I think it was Irina Kalchu's dissertation defense or something. And it was right around Halloween. I think literally I was at Brown on Halloween. And Morris was dressed up, I think, as a vampire. It was great. Yeah, I think he was a vampire. It was awesome. This is what I mean. He's very, very kind of playful guy. Very serious when it comes to contributions to the field, but takes himself very lightheartedly. So at some point, they came up with this transactional memory idea. I can't remember when the original paper was published, but let's see. Oh, sorry. It was, yeah, Morris and Elliot Moss. Is that what I said? Yeah, something like that. So this is the paper, 1993. Transactional memory architectural support for lock-free data structures at ISCA. Okay. And then look at this. Here you have software stuff for C++. C++, this. So I was at least peripherally involved in this. And then I was also involved in this a little bit. Oh, what is this? And newer until removed in Comet Lake. Okay. So I can talk a little bit about the transactional synchronization extensions, as well as restricted transactional memory, RTM, as they called it, I think. And Arena and I think some others, I think we built maybe one of the first hybrid transactional memory systems for Intel, that we did the software side and then we invoked the hardware side in the TSX RTM stuff, and then we published a paper about it, like the Envisewell paper, I think. There's a lot of papers, there's a lot of stuff, so I'm not going to remember all the details exactly right. But anyway, so this happens in 93, and then maybe in 2004, 5, I take a class on parallel computing taught by my co-advisor, Manish Vachaharajani. And I've taken parallel computing before, so I knew some of the stuff. But at some point in the class, we started talking about transactional memory, and immediately I kind of perk up because I've never heard of this thing before. And I think this is quite interesting. So there were a few reasons why I was originally pretty excited about transactional memory. The first is, and maybe I'll write this down, and this is maybe just a high-level view of kind of the way I think about things. And I'm not saying that this is the right way to think about things. This is just sort of like how I think about stuff. So Manish is teaching transactional memory, and the first thing is it made sense. He was explaining it, and I think he did a brilliant job. I think he's a brilliant instructor and advisor. Like, Manish is fantastic. Actually, yeah, this is Manish. He disappeared. Anyway, yeah, I wonder if we look at... Yeah, so Manish, yeah, I think he did his PhD at Princeton. And there's probably some papers on here. Yeah, here's one paper with yeah, me, Manish, and Jeremy all together. And there's probably other papers in here, I suspect. I think we did a bunch of stuff. Some of them are like workshop papers. Okay, who cares about that? So when Manish is teaching this, Manish with a beard, without a beard, with a beard, without a beard. Oh, look, hey, here's me. So, yeah, and I think this is one of their companies. This is John Giacomo, and that's Manish. And this guy, I think he was the person they brought in as the president or something. Oh, and look, here's Jeremy. This is Jeremy Seek. This is my advisor. Excellent. And by the way, Jeremy's, at least at the time, deep participant in C++ as well, which is part of the reason why I was sort of drawn to Jeremy at Boulder. Is he had done really incredible work in C++ with the Boost graph library work, I believe, and other things. I think concepts, C++ concepts, is partially like his brainchild. I think also TypeScript is something that he was involved in, because it's like a gradual typing thing. Let's look this up. Concepts. Seek. Yeah, look at this. See, there's so many rabbit holes we can go down. Yeah, see? Ha! I remember. I remember he and I were talking about this, and I think concepts is being accepted into the standard now, I think, but there were some challenges initially, and some of them I think it's just sort of typical standards stuff. When you start working on standard languages, there's the committee, and there's only so many features that they can put in for every rev. There's a lot of stuff, I guess. And I remember this is actually before I got involved with transactional memory. into standard C++, Jeremy was telling me about some of the concepts efforts. Yeah, because I graduated from Boulder in, well, unofficially, I think in 2010, but officially, I walked, I guess, in spring of 2011. I think that's what it is. I don't remember these things. But so this is in the time span that I was working with Jeremy. And he was telling me there was some complexity getting this in. So what the concept's effort was, as I recall, is it was trying to sort of make sense of some of the template errors that you get from compilers. And for those of you that were coding 15 years ago, when he's working on this, you may remember the template errors you would get, which would be super hard to understand. I wonder if he has an example. No, he's got his typical theoretical computer science stuff where I think we talked about this and how we look at these are like state transitions, and these are various like lambda calculi. Anyway, again, there's a bazillion different rabbit holes we can go down. I'm going to try to keep us slightly on course. I was really hoping that he would show an example of some of the errors, because they were pretty bad. Okay, so maybe it's in. Oh yeah, here we go. Yeah. Okay. So look, this is the. Yeah, go away, dude. Adobe. You're in my face all the time. This is the kind of stuff that you would typically see, I think, before concepts. Like, what is all this? And notice too that the errors that you would get for templates, they're in the template files. They're not even like in your code. So you're led to believe, oh, is there something wrong with the actual standard? Are the template implementations in STL wrong? No. I mean, maybe, but that's generally not the actual problem. It's just that the way template programming works, especially when you're just using templates, is templates are a framework to think about things, but in some sense, the code that you see for templates, function templates, class templates, that code doesn't sort of like really exist. It's kind of important to understand this, is you see the code and it exists to you, but from the compiler's perspective, until the point that that code is instantiated with a type, it doesn't actually exist. It's like the compiler is going to just say, there's no code here. So then what does that mean? Well, when you start to instantiate them with types, then in place in these files, it then basically does substitution of the types for the templates in place, which is why you get things like these errors in STL algo with these random access iterators and these no match thingamabobs. And this was the point that I think Jeremy was trying to make, is like the average human being that's just trying to use the STL that doesn't like massively grok templates. And templates, I think they're super powerful. I actually love template programming because you're allowed to write code that is very small, has a very small footprint, but it can be used in a variety of ways. Hundreds, maybe thousands of different ways with all these different types. And so in some sense, like a superpower is you're writing a function, but you're not writing a single function. You're writing like 10,000 functions. And personally, I think that's pretty awesome. I love that. I think that's very powerful. But when you're writing these template functions, and then people start using your stuff, they're going to get these types of things. And then who can make sense of whatever this nonsense is? And oftentimes, you have to get into this part here, this error 1 on CBP. This is the problem. Actually, the truth is, in this case, it's probably not even that this might be the problem. It might be the problem exists in the type that's being used here, and then it doesn't have some operator. Like, one of the most common ones is people try to use types for containers and they haven't implemented like the less than operator, right? And then you get all these cascading errors on like, where is this fails because there's no less than operator, and it looks a lot like this. Okay, so I've meandered a little bit down this strange rabbit hole, and now I'm gonna like maybe back us up a little bit. And to keep in mind, this is actually really important, because Jeremy was explaining some of the stuff that he was dealing with the standard committee, and I just kind of thought like, yeah, Jeremy's a superhero. I'll never be doing anything like at the standards level, and wow, he's amazing. And I just kept working on transactional memory stuff. And then at some point in that effort, maybe this is it. What are we looking at here? Okay, so this, I guess, is part of here's me, and then here's like a list of a lot of the people that were involved. I want to be super clear. I was not the most involved person in the transactional memory effort for a large majority of the time. I think I was, and again, I don't quite remember because it was quite a bit ago, but I think I was the chair of the compiler specification group that was a research group between Intel, Sun Microsystems, and I feel like I'm forgetting somebody. Oh yeah, I could probably just look at the names here. So Hans, I think, was at HP Labs at the time, so he was deeply involved. I was at Intel. Victor was at Sun. Jan was, I forget where Jan was. Paul is, I think he's now at Meta, but I think maybe he was Sun. Like a lot of these guys, Magid Michael, he was at Sun. Mark Moore, Sun. Torvald, I think he was AMD. Yeah, okay, cool. So, and then Michael Wong, IBM. Michael Scott, academic. Tatiana was Intel with me. Mike Spear, professor at Lehigh. And what's really interesting is that Mike and I were probably maybe the most junior people in this group, at least junior in terms of, a lot of these folks are these super PhD whatever folks that are doing incredible things. And then Mike and I were just working on transactional memory in grad school, which is how we met. Is he was doing some really awesome work, and I was super impressed, and then we met at a conference and we just started sharing notes and things. So I think I got involved with the transactional memory effort first, and then once we converted the compiler, the research compiler specification into an actual movement to standard C++, then Mike got involved. I think Michael Wong took over as the chair. I think at that point I became the vice chair. Michael Wong took over as chair because he was a longtime contributor in standard C++ and other things like involvement, I think, in OpenMP. So he knew the standards committee really well. And so he was, I think, the right person to chair the effort once we switched from this research compiler to, okay, we're an actual study group in C++, and we want to get transactional memory into the language. And then my involvement so I'm thinking about pivoting back to what I was explaining here. Let me switch back to this real quick, and then let me continue on where I started to get involved. Okay, so transactional memory made sense to me. I really liked what it was proposing. And I could see how it simplified things. And what I mean by that is probably like this. So this is an example of a transaction, I think, in C++ for the way it was being proposed. And all you have to kind of do is just say, this will be synchronized, and then wrap it with these curly things. And that is a potential significant leveling up of parallel programming, at least at its time, because the best that we kind of had at that point was like mutual exclusion, coarse grain or fine grain locking. And coarse grain locking could be maybe as simple as this. Like you have one global lock. And I think there's a couple languages, like I think Python had at some point the Python single lock or something. And I think actually even the Linux kernel had something like SGL, the single global lock. And I'm probably misremembering this, so feel free to correct me in the comments. But the point is that coarse grain locks could be potentially as simple as this, but they're really inefficient. Everybody stalls. Hey there. Everybody kind of stalls on one thread of execution, even if there's no sort of overlap in the execution, in the shared memory. So then the alternative is fine grain locking, which makes things significantly faster, but it's way more complicated. It's so hard. It's so hard to get right, especially as you cascade deeper and deeper into the fine grain locking, and it's very easy to create deadlocks. Super easy. And deadlocks are basically like one of the worst things you could possibly run into. Live locks are probably worse than that, but live locks generally, I mean, they can appear with mutual exclusion locks, but they mostly appear when you're using non-blocking data structures. So wait-free concurrency, things that have single atomic operations that do small steps forward on things, and then it's like they keep kind of canceling each other out, because they make one step over here and they start moving forward, but then this guy over here starts making one or two steps forward, and then they both realize like, oh, you should go, and so I need to unwind all this stuff, and then this guy says, oh, you should go, and I should unwind all this stuff, and everybody unwinds, and then they start again, and they collide, and they start again, collide, and then what happens is your CPU ends up getting pegged, So it looks like something's happening and nothing's happening, because they're just like, do stuff, undo it, do stuff, undo it. And so that's a live lock. And that's really bad, right? But maybe the next close as bad thing to that is something like deadlocks, where the simplest example is, let's say you have two threads of execution. So we'll say this is like thread 1, and this is thread 2, and this guy is going to acquire lock A, and then lock B, and then do a whole bunch of stuff, and then release those locks. And this guy over here is going to acquire lock B, and then lock A, and then it's going to just do stuff and then release. And so if these operations happen where it's like, this is time step 1, and maybe this is time step 2, just to make the math simple, and then this is time step 3, and then this is time step 4, this is a deadlock. So what happens is you start here in T1, and then this lock gets acquired, and then T2 over here, this lock B gets acquired, and now both systems are halted, because this first thread can't acquire lock B. Can't be done because thread 2 has it, and thread 2 can't acquire lock A because thread 1 has it. And so they both just kind of wait and say, well, I'll wait until it gets released, and neither of them are going to release it, and so your system is deadlocked. Deadlock is, you really don't want to have this. And one of the beautiful things about transactional memory that immediately made sense to me is that you can design transactional memory systems so they are deadlock free. They will not have deadlocks. You can actually prove it, that they won't have deadlocks. It's much harder to prove that transactional memory systems won't have live locks. And in truth, a lot of the early TM systems, especially those built in wait-free synchronization, they would have live locks. And a lot of that would be like the contention manager battles, which is a very long story. So I don't think we can get into that in this episode 1. We'll get into that at some point. So one of the key promises is it made sense in that you can avoid deadlocks. And that's a really good promise. And that's basically built at the transactional memory level. So what's so awesome about it is with transactional memory systems, the people using it, they basically don't even have to worry about this. They could just say, synchronize this and synchronize that and synchronize all this stuff, and this TM system would say, I will never deadlock, I promise. And then I will try to make these things function as efficiently as possible, which is, I think, if I recall correctly, it's like this idea of optimistic concurrency, is that you go sort of under the premise. So there's pessimistic concurrency, and then there's optimistic. Pessimistic is like mutex locks, which says, like this thing, is I need to acquire all these locks because this code here could conflict with somebody in the world. So I need to get in front of that and make sure that doesn't happen. That's pessimistic. And then what happens in the real world is oftentimes like this guy is messing with this global variable x, setting some value, 10. And then this guy over here is messing with global variable y and setting it to value 11. And if they're messing with different global variables, yes, it's shared memory, but there's no overlap. There are not actual conflicts in the memory subsystem. These can execute concurrently without any synchronization. But you don't know that ahead of time because maybe that's just one of the paths. So instead, what you can do is you can use optimistic concurrency, which says just let the stuff run, and then at the end of the transaction, try to figure out if there was a conflict or other things. It's more complicated than just that, but like in my dissertation, I focused on doing commit time invalidation, which basically says wait until you get to this bracket here after this thing is run completely, and at this point see if there's conflicts. But there's other systems that do early exiting of the transactions where they would like say, okay, try to do this and immediately check, is this a conflict? One of the, if I had a reasonable contribution in my dissertation, it's probably that I tried to show you can build really fast transactional memory systems if instead of validating the transactions at every point where you perform an operation in the transaction's lifetime, instead only perform the validation, or in this case, invalidation, at the point of the commit. Just do it once. And then on top of that, you have a flag from the transaction at any point that says, oh, you've been invalidated. So what would happen is in the historical systems, every time they do an operation like this, they would run through a full validation of their memory to see if anybody changed stuff, if there's conflicts. And then if they get to the end, then they know they're in the clear. The system that I built is, it basically would say, just assume that it's all going to work and write it off to the side. And then when you get to the end, check to see if there are conflicts with these other threads. And when you check, you make a decision. Should I go forward or should they go forward? If you decide you're going to go forward and there's conflicts, then what you do is you flag the other transactions that are in flight and say, you have to stop, you have to stop, you have to stop. Okay? So then in those other transactions, the only thing they have to do each time, and they don't even have to do this, they can literally just run to the end and then stop, but you can have early exiting, which can save a lot of work by just checking the valid flag. So each of these transactions has a valid flag of like, am I valid? And by default, everybody's valid. And the only time they become invalid is when the transaction that gets to this phase and commits, if it comes in and says, I am going to commit, and in order to do that, we have a conflict, so you have to stop. And then you have to stop. So what it does is it sets all of their valid flags as to false. And so they can wait until the end to look at the valid flag, or they can just check every time they're doing a memory operation and say, hey, am I still valid? And that's just O of 1 overhead. Whereas the way it was done before some of my research, it was O of n overhead each time you did full, what they call opacity checks in the transactions. And because you're doing O of n times, it's n squared. So, like, I mean, O of 1 is less than O of n squared, right? But, to be fair, one of the things that you have to do that is a real problem is at the transaction's commit point, it has to grab a global lock that stops all the other transactions from making forward progress. Or so you are led to think from a kind of naive perspective. And by the way, this is why I think a lot of the folks that were senior transactional memory people kind of shied away from this. Is I don't think that I'm the first person to think of commit time invalidation. I think there were lots of people before me that were way smarter that thought of it, and they thought sort of with maybe only 1 degree of separation, which is when this transaction gets to commit, in order for this to work, it has to stop the forward progress of all the other transactions. So no one else can commit while it's committing, otherwise the validation checks don't work, right? And so at first glance, this sounds like, why would you do that? That's like coarse grain locking. And so you're back to the slowness of coarse grain locking. Well, it turns out, in reality, you don't actually have to do that, because the only transactions that need to actually be checked are the transactions that are performing write operations. Read transactions, when the transactions are performing read only, because you're performing all these operations potentially off to the side, those transactions basically they never need to check, and the only thing they need to essentially check is when they get to the end here. They don't even need to do global lock. They just need to say, am I valid? And if the system says they're valid, they're like, done, I'm done. And when you consider that a lot of transactions are read-only transactions, they're like, think about database querying. I mean, the read-only part is sort of in the name, right? It's a query. It's not a write. How many database queries are there versus database updates? The majority of like database queries versus updates, the majority are the queries. It's just reading the state. That's why we have things like Redis, right? Redis was like, wait a second, what if we had databases that are essentially only read-only? How fast would that be? I kind of made the same observation, is that for systems that have heavy amount of contention and heavy amount of writes, commit time invalidation is not super great. But for other systems where a small minority of the transactions are performing writes and the large majority are reads, this can be really fast. And in cases where all the transactions are reads, this thing, it's almost like you don't even have any locks. You have nothing, because you get to the end and you see they're valid, and everybody sees they're valid, and there's no stopping on any transaction. And in those cases, commit time invalidation is insanely fast, which is, I think, what we saw in the real world is most of the cases that existed in the wild were the cases where there's not many writes, and in many cases where it was actually read-only, which is why commit time invalidation, I think, is sort of one of those really non-intuitive things where at first glance it looks like, this is so dumb. Why would anybody do this? And then after you peel back the layers of the onion, you start to realize, wait a second, this could be actually really fast. You just need to, like we were talking about in some of the former episodes, one of the traps that I think people fall into is when they have a problem, they just look directly at the problem and think, I need to solve this problem. And so their sphere of thought is limited to this. What I often find is that for any problem in any space, you have multiple sort of spheres of control, and the further out you go in the degrees of separation to this thing, the more interesting the problem starts to get, and you often have discovery of potential solutions maybe that other people might have overlooked because they're only focusing just on this inner sphere, which is just the core problem. It's like, let's solve everything, rather than saying, well, this is not going to be super great for these cases, but then in reality those cases are so small it doesn't even matter. And for the cases where those do exist, just use the other stuff. So anyway, I think we're almost at our 15-minute point where I need to stop, so YouTube will do translation to all of its 20 languages or something. But this is our starting point for transactional memory. We've meandered quite a bit, and we've kind of followed almost no flow, except that we know the field was sort of started by Morris Herlihy, Elliot Moss, and Nir Shavit, and then at some point I got involved. We'll say that was around 2006, something like that. And my involvement from 2006 until about 2015. And in that 9-year span, one of the things that I ended up working on was this thing, to try to get transactional memory integrated directly into C++. And I was looking this up just before going online, and I think we'd have to probably talk to like Mike Spear or Hans Bohm or Michael Wong, some of the other folks that I was pointing to in that PDF, that this guy over here. We have to chat with them to see what the current state is. I think some of those folks actually may be watching GTT, so if you are watching, guys, feel free to drop in the comments like where transactional memory actually is right now. But what's great is I think it's been accepted as an experimental feature in transactional memory as of 2015, I guess. And so there are some compilers that actually support this today as an optional experimental feature. So just to be clear, what this means is that compilers for standard C++, they are not required to implement transactional memory, these synchronized blocks. They don't have to be a standard compliant compiler. But if they want to, they can support this experimental feature. And I think that what I saw at some point was GCC and G++. It's kind of sort of ish a similar thing, not exactly, but they had implemented it. And I think that was like I can't quite remember exactly how this works. My friends that are far smarter and know about these things more than I do can speak on it, but I think it was like supported by Clang or something, and that was cool. I don't know. I'll do some research actually after this, and we'll go into a little bit more detail next time. So this is our first step forward on this. Here you can see this is in the what did we decide? 1990s? Something like that. And then 15 years later, I heard about it, and then I started getting involved, and then we got to this point. I would love to see transactional memory actually integrated directly into standard C++, and maybe, just maybe, in my lifetime, it will happen, and I'll feel super accomplished in the sense that something I worked on in a very small way actually got integrated into an ISO standard conforming language. And also happens to be my favorite language, which is C++, as I think most of you know. So that's pretty cool. Anyway, that's all for now. Thanks everybody for hopping online with me or watching the VOD. And feel free to drop any comments about stuff in particular you want me to talk about with transactional memory moving forward. And thank you again, Untranslatable Metaphor. I know you've been super patient. I've got you, brother. We're getting there. Okay. Keep growing.